I did something in my life.
Okay, so again, if we multiply this row by this column, that means we match up the first number with the first number and the second number with the second number, do those multiplications and add the results. That's the definition of row times column, which we talked about about last Thursday. And the meaning of this is if S is your number of sane, D is your number of demented, you have the original transition percents, 10% of your sane becoming demented, 20% of your demented becoming sane. That means, well, if 10% of your sane become demented, then you retain 90% of your sane. So you're going to multiply 0.9 times your number of sane and add 20% of the number of demented, and that gives you the new number of sane people. Similarly, 10% of your sane will become demented, 80% of your demented will remain demented. So if I multiply this row by this column, I'm going to get the number of demented, right?
Mm-hmm.
So the way this multiplication comes out, I multiply the first row by this column and I get 0.9s plus 0.2d. I multiply the second row by the column, I get 0.1s plus 0.8d. Number in the first row, the numbers in the first row multiplied by the column go in the first row. Numbers in the second row multiplied by the column go in the second row. Okay? So now, how do you think we're going to multiply this matrix by this matrix? Remember, we multiply rows by columns, right?
Mm-hmm.
So how many rows times columns, how many row times column products can we find out of this? Four? Yeah. First row times first column. First row times second column. Second row times first column. Second row times second column.
Yeah.
Well, that's relatively straightforward to write out. You know, the interpretation and the things you can do with this, you wouldn't believe where this goes, okay? Extremely powerful. But anyhow, we do first row times first column is going to give us 0.9 times 0.9 plus 0.2 times 0.1. That's the first row times first column, right? So row 1 times column 1. Okay? Now we're going to do row 1 times column 2. Where should I write that down?
Write it below.
Second,
I'm sorry?
right below.
Okay.
No, you'd want to write it across.
Yeah. I'm going to keep it in the first row since I'm multiplying by the first row.
Yeah.
I'm multiplying the first row by the second column. I'm going to put that number in the first row and the second column of my new matrix.
Yeah.
Okay? So I'm going to do 0.9 times 0.2 plus 0.2 times 0.8. So that's row 1, column 2. Because it came from row 1, column 2, I put it in row 1, column 2. Does that make sense? Mm-hmm. Okay, well then I've got my rule. I can multiply any compatible matrices using this idea. If it's got rows that are 48 numbers long, as long as the second matrix has columns that are 48 numbers long, I can multiply it. And I always know where to put the result. Whatever row I use in the first matrix, whatever column I use in the second, tells me what row and column to use in the product. Okay, well, then the second is going to be 0.1 times 0.9, you know, matching up the 0.1 and the 0.8 with 0.9 and 0.1. I'm going to get this. And the last row, second row times the second column is going to be 0.1 times 0.2 plus 0.8 times 0.8. Okay, well 9 times 9 is 81, 2 times 1 is 2. That's going to give me, when I add these up, that's going to be 0.83.
Yeah.
When I add these up, it's going to be 0.18 and 0.16, which is 0.34. Okay. When I add these up,
17.
I get 0.9 and 0.8, which is 0.17. And I get 0.02 and 0.64, which is 0.66. Okay? Now what this is, this could be determined as a, this could be interpreted as a sane dimented matrix, where 83% of your sane stay that way and 17% become demented, and 34% of your demented become sane and 66% of your demented stay that way. Okay? So this would be the result of two transitions. If I multiplied this out and then multiplied this result by the same matrix, this is what I would get. Okay? Now, when we go over to the computer lab, in addition to doing things with Excel, Excel is not a mathematics program, it's an accounting program. You can torture it into doing some mathematics, but it's not inherently a mathematics program, and it can't do much. I mean, it can do quite a bit of what you need to do, and probably will for the next couple of years, but I want you to also see at least something about a mathematics program, which is, and we're going to use Wolfram Alpha for that. In Wolfram Alpha, okay, well, first of all, if I type this matrix, and I've shown you this before, so I'm not, this matrix, this transition matrix is like this. Commas between numbers in a row, semicolon separating the rows. Wolfram writes it like this. No semicolons. Okay? Now that's written down on your paper, I tell you that. It's just the way Wolfram chooses to write its stuff. Now Wolfram is a list processing language, and that's the way you do lists. There's a reason for that. You don't know what that means and don't need to at this point. Okay? But that is the reason. Okay.